Shall I begin?
Okay, so we're very happy to have Ritabrata Bhattacharya. Today he's going to talk to us about some work he did at Utah University on classes superconformal indices from maximal supergravity. Please.
Thank you, Shanmuga. Am I audible at the back? Thank you for giving me this opportunity to present my work here. I'll be talking about classes superconformal indices from maximal supergravity. So this paper came out in November last year and it's been accepted in PRL. This is a work in collaboration with Dr. Oscar Varela, who's a faculty in Utah State University, and his student Abhay Katyal. So here's a brief outline of the talk. So I'll start with a bit of motivation for why we are interested in the problem that we're going to talk about. Then I'll flash the main results of our paper and also state some of the implications of those results. And then I'll go into a bit more detail I'll talk about the setup in which we do our computations and stuff, and describe at least some part of the computations when we talk about the spectrum of our theory. And finally, I'll end with a couple of future directions. So let's dive right in. So the classification of superconformal field theories that resides on M5-brane world volumes is an outstanding problem in string theory. Now, why M5-brane world volume? Because we know that there are no consistent interacting superconformal field theories beyond 6 spacetime dimensions. And M5-branes precisely have 5 plus 1, 6 dimensional world volume. Now, this problem is broad and quite general. So what people have done or have been able to tackle is more tractable limits of this problem. For example, wrapping a stack of M5-branes around punctured Riemann surfaces sigma, where this sigma is a part of the your compact surface, with a suitable topological twist, this leads to an infrared fixed point that is described by a 4D n equal to 2 superconformal field theory. And these class of superconformal field theories are called class S SCFTs. This was described first by Gayatto, and then there was some work on this by Gayatto and Maldacena. M5-branes it's like a brane in M theory, which is like it's your fundamental objects like strings and stuff. They end like in string. They end on D brane. So these are also some objects in M theory, which have like world volume. I think so. If there are like more subtle these things, I won't be able to tell, but you can think of it like that. M theory.
Don't have a even a description. Describe them as black holes. The M theory has this default fields there, right? Default. So correspond the default field couples to a 2-dimensional one volume, 3-dimensional one, right? World of fields couples to a 6-dimensional one. So by definition, this is the BBS, the supersymmetric version of that, right? That's the only way it is defined.
The motivation you're coming of your problem is, can we, I mean, if I take this M5-brane and theory and do this U1 compactification, you get it type 2 or type 2, right?
Yes.
But so you can motivate the problem from that perspective also, right? From the 10-dimensional theory perspective.
Yes, there are ways to compactify or have truncations to 10D theories as well, but we won't go here. What we'll do here is directly take 11D and we'll talk about the compactification of the 11D supergravity. That will be sufficient for the purposes of this talk.
You said some statement about the superconformal field theory, like only maximal dimension is 6 or something.
For interacting superconformal field theories.
More than 6, we can't have any theories.
More than 6, you'll probably have free, if I'm correct, but no interacting superconformal field theories beyond 6. So one of the key properties of these classes theories is they are naturally strongly coupled. So typically in most cases, they lack a Lagrangian description, and you have to talk about the properties in the context of equations of motion and so on. So there are many tools to handle this kind of situation, one of which I'm describing here. Say the duality, it helps in extracting many useful information about these theories without ever having to refer to a Lagrangian and so on. As an example, one can talk about the superconformal index, which is a quantity closely related to the partition function, but not exactly the partition function. So the superconformal index in various limits can be computed for these classes CFTs through the 4D, 2D dualities that they execute. So these theories enjoy known dual gravitational descriptions through ADS CFT correspondence. The simplest such construction was done by Maldacena and Nunez. This was what they got was a half maximally supersymmetric, that is n equal to 4 solution of D equal to 11 supergravity in 5 dimensions. And this is the metric, like for their solution, this is the metric that we have. So we see that this is of the form ADS5 times a fibered space where this S4 is fibered over the Riemann surface sigma. So here is the ADS5 part, it stands by itself. And when I say S4, I mean these coordinates theta, Z, and the coordinates that you use on S2, they all together form the S4, and this H2 describes the Riemann surface that we are talking about, the hyperbolic space sigma. And this V, these are like one form, which is a function of the H2 coordinates. The differential of V, dV, gives the volume of Riemann surface. And precisely this factor, or not factor, but precisely this relation that you have the V sitting here makes it a fibered space. So if this V was 0, this would simply be a product space. That's why this V takes into account the vibration and so on. And this sigma, just let me mention, is a constant curvature Riemann surface.
So here you have already got the VR horizon.
Yeah, probably here, when they describe a near horizon limit. That's what
wrapped on some Riemann.
Yes.
Where is the Riemann surface?
This H2, that is like the sigma. Probably a bit bad notation.
There's the ADS5 and then there's a theta and
the Z coordinate.
The three coordinates are theta and H2.
So H2 is the sigma, the coordinates on H2 are the sigma. Oh, yes. The Z is one. H2 is. Oh, V is like a one form on, like it's the vector is a function of H2 coordinates. That's what's doing the vibration. So if this V was set to 0, or another description is that the differential of V, dV, gives you the volume of the Riemann surface.
It's like this M5-branes wrapped around this Riemann surface sigma. Then we are looking at the near horizon geometry of that.
Yes.
Yeah, the solution in 11 times.
Yes. This construction has been generalized along different directions by these authors. For example, people talk about also n equal to 1 SCFTs and so on. But in each case, what has been observed that the dual SCFTs of classes, at least, they arise as a combination of the building blocks. And by building blocks, we mean the superconformal field theories on a 3-punctured Riemann surface. Now, the way at least I understood this is that in the IR, Riemann surface sigma with genus G and some punctures, it degenerates to a pair of Pan's decomposition, which is like 3 punctured spheres and joined by a thin line along the cuts or the punctures.
So the statement that if you think of the Riemann surface as being glued, constructed from glued 3-punctured spheres.
Yes.
Right? That of course you can always do.
Yes, yes.
And then you take the SCFP on those three punctured spheres.
Yes, and that gives you the
So there is some
superconformal.
algorithm by which you can construct the SCFP associated with
In these works, they do provide some details about this thing that I'm not very familiar with. But I remember the statement that they make is that where they think of this Riemann surface as three, glued three spheres with three
That's of
spheres.
course you can always do.
Yes,
But I'm
yes,
just saying as SCFP,
yes.
right? How do you get the property of the actual SCFP on sigma from property of the SCFP on these three punctured spheres?
You mean
That's the superconformal index, right?
yes, yes.
Of the SCFP on sigma. Is it possible to get it for superconformal index of SCFP on the punctured spheres?
I
That is a very strong statement, right? You can, as an SCFP, you can get.
they probably have to you have to do something with the modulize as well, right? But that's what you are talking about.
Yeah, but I would think that the index will be independent of the model, right?
Okay, okay, yes, yes.
So the topology which will be relevant.
So what is the idea? You take your Riemann surface and you have a pair of spans decomposition.
Yes.
And so there's some way of gluing pairs of spans to get this Riemann surface. And that corresponds to a way of gluing the SCFP to get this new SCFP of this bigger surface.
Yes, at least that's my understanding from looking at the what?
Can you just maybe Ashok's question is roughly can you indicate how that works? So let's say I give you the SCFP.
Yes.
I tell you all the correlation functions everything. So now how will you get this SCFP or this bigger Riemann surface by gluing these together?
Like the CFTs on each Riemann surface is like the one that was described by Gato. There is a CFT on three punctured Riemann surface.
But from there to glue two superconformal theories together.
Yeah, like I don't completely know about this part when when I looked at those papers, I didn't completely understand how this gluing prescription takes into account for the rest of the part. But in our case, we won't be doing this gluing or such a stuff. In our case, we'll take the approach and we'll use a tool which is called the exceptional field theory to compute the spectrum. That I'll describe in a minute.
And the goal of these punctures is some flavor symmetry. I vaguely remember something like that.
What the role of the
Punctures?
Yeah, for the punctures, it does play some role for the flavors, but in our case, we'll work with a Riemann surface without punctures. But genus, what?
Flavors.
Like the number of punctures will be like if it's a SU flavor, like SU n flavor, n is the number of punctures. That way.
Why you didn't say anything about flavors? Maybe you did have that.
No. I have not said anything about flavors.
Yeah, my memory is that it will be a superconformal field theory of some gauge, right? If you have n of these, you will get some SUN. And the punctures somehow capture the flavor. How many formulas of each kind you have? I don't know remember what this story is.
But the punctures, there's three puncture Riemann sphere is going to be, many of these are going to be stuck together. So in the end, you will just get some smooth Riemann surface, which might not have any punctures.
So just take the SCFP for three puncture Riemanns.
So
That's the simplest one, right?
Okay, so let's take
That should correspond to some theory, some SCFP.
I see. But what if I take it and I glue lots of them together so I get a completely smooth surface? Because for any Riemann surface, I can do a pair.
Yeah, then probably it will be there will no flavor or something. No flavor symmetry or something. But okay, I don't know remember what the exact correspondence is.
I see.
Because normally when you think of Riemanns are compactifying on something, right? You don't include punctures.
I see. Okay.
Right?
I see.
Because consequent mechanism doesn't have surface with punctures.
Right. I see. Now, a specific limit of the index, which is called the Hall-Littlewood limit, or these SCFTs, at large n, by n we mean in the work that I'm telling here, is that they use
SCFT is equal to what?
this
This is the
this ADS5 in the boundary, you have a CFT, but you also have supercharges. Yes.
And if you just take a T2, it becomes N equal to 4 supersymmetric elements, right?
Okay.
In M5, then the Riemann surface is T2.
I see. Okay.
Then time is just N equal to 4.
Yes.
So, let's see that.
Yes, but doesn't torus break no supersymmetry? If you compactify on torus, isn't you get unbroken supersymmetry, like no supersymmetry?
Torus compactification doesn't break it.
Right.
So yeah. So there I think that you get N equal to 4 superangles, and then the exchange symmetry of the two cycles of the torus, that becomes the S duality of the.
Oh, I see. Okay, I see.
The boundary of this ADS file is just S3 plus time.
The boundary of the ADS5? Sigma. Yeah, the sigma is part of the internal space.
The boundary of the CFT is always living on S3 cross R.
S3 cross, yeah, 4-dimensional, right? 4-dimensional boundary.
I guess you can take ADS5 other than global coordinate or.
Yeah.
In 3 plus 1. CFT is
always in 3 plus 1.
Yes.
And when you said the SCFT of the constant Riemann surface, that was 2 dimensional.
Yes.
What does that mean? You give me, at the next slide, you said give me the SCFT in 2 dimensions. So could you go to the next slide?
Oh, yeah.
Yeah. So dual SCFT arises, which is the SCFT of 3 constants that we do. The dual SCFT is in 3 plus 1 dimension.
Yes.
Yeah.
The second SCFT in the second part, that is on 3 constant Riemann sphere. What does that mean? That seems to be 2 dimensions.
What I mean here is that the spectrum of the SCFT, that is corresponding to a theory where the compact space is 3 punctured Riemann surface. 3 punctured sphere, sorry.
I was thinking somehow you have a conformal field theory on and you do a pair of bands decomposition, but that's not what is happening.
No.
You have a conformal field theory which corresponds to conformal field theory for a particular 3 function.
Yes.
But a conformal field theory is 3 plus 1.
Yes.
But I think there is also this ATT correspondence which relates it to the conformal field theory on this on the Riemann surface.
I don't know.
41.
Like 4D 2D duality?
Yeah.
I know of that duality, but I don't know the details of that. I know they use it heavily in this n equal to 2 superconformal index for n equal to 2 theories, but I've not actually worked out any example of such.
So here what you are saying is this 3 punctured Riemann surface
Yeah.
doing is the sigma there, but the conformal field theory lives in 3 plus 1 and boundary of the area.
Yes.
Yeah.
This is actually quite confusing. Maybe this would need to be because you get one CFT for one compactification.
Yeah.
You're saying for other compactifications you get a related CFT.
Like the spectrum would be different there, right? Like the conformal dimensions will be. Yes. But it lives on the 4-dimensional boundary of this ADS file.
It's probably not doing standard, right? There is some algorithm by which you construct the correlation function of this in terms of the correlation function of this.
So seems to be good. Okay.
Yeah.
The idea is that all these correlation functions can be thought of as some correlation function on the end, right? 6-dimensional. And for 6-dimensional theory, there is fluid. You can apply that, right?
Yes.
And that must be what is going into this relationship. So now reinterpret the 6-dimensional correlation functions in terms of this. correlation path in the 4T CFT. And 6 galaxy relations will descend down to the 4 galaxy.
That's also very confusing to me. If I take combat direction, it just and I break it up into 2 line segments. That I can call it. I give you the spectrum on that compactification. That is not the same as I'm giving you the spectrum on the circle.
Yeah, true. But maybe that is what constant.
Okay, that is what is something. Okay.
Yeah, so like I mentioned, this Gadde, Rastelli, Razamata, and Yan, they consider SUN quiver gauge theories, and the all Littlewood limit they were able to compute in large n limit. In their work, they also talk about the other limits of the n equal to superconformal index, but those are only at finite n. The results they are only at finite n, and only the large n we can match from this ADS-CFT correspondence. So until now, a calculation from the supergravity side had not been attempted. So this was also one of the key motivations for doing this exercise. So we observed that the d equal to 11 supergravity admits a consistent truncation on this fibered space sigma fiber S4 to maximal n equal to 8 supergravity in d equal to 5. This was the observation, and in this language, the Maldacena-Nunez solution that we said, which is the ADS5 times sigma fiber S4, this solution in this language arises as a spontaneously supersymmetry breaking vacuum.
This statement is super any sigma that there is a consistent truncation.
Any sigma which admits a hyperbolic metric like a Riemann surface. Yes.
And yeah, in that consistent truncation, what will do? Do I anything that depends on the sigma coordinates, or it's more complicated?
Well, we will see how the effect of the sigma seeps into the Kaluza-Klein mass spectrum. When we describe the spectrum, it will become more clear. But
what do you mean here by consistent truncation? Like we can throw some fields without affecting.
Consistent, yeah, like the solution for say. So this is like this solution describes d equal to 5, n equal to 4 solutions, right? So a solution of that is also a solution of this maximal supergravity. That's what it means by consistent truncation. And once you have the maximal supergravity, I think there are ways you can uplift it to and show it that is a part of a d equal to 11.
Some correlation functions of those decouple from the.
Yes.
Yeah, so any solution of the truncated theory is a solution of the original theory. But of course, that doesn't generate all the solutions. Yes. That's what Rogers guarantees any solution of the truncated theory is a solution.
The existence, and now this is one of the implications of this result, that the existence of this maximal truncation severely constrains the spectrum of Kaluza-Klein fluctuations of d equal to 11 supergravity about this vacuum, around this vacuum ADS5 times sigma fiber S4.
So this consistent truncation has been proven that there is a consistent truncation?
Yeah, this we observed, like when we did the computation, we observed, and I'll tell.
You observed that all the additional fields come quadratically or in the action. What did you observe in this?
So I'll describe later, but when we use this exceptional field theory story, use a generalized geometry to uplift to d equal to 11, there's a quantity which is called the embedding tensor. We find that it is constant. By constant, we mean it can depend only on the parameters like the S4 radius or the constant curvature of the Riemann circle, which can be set to some constant values. And that can only happen for a maximal supergravity, and that's how we know it's a truncation to maximal supergravity.
This will describe later.
Yes. This I'll describe in the setup. Just flashing the results here. So the existence of a maximal truncation severely constrains the spectrum of the Kaluza-Klein fluctuations about this vacuum, and allows us to compute the full spectrum of light operators using some spectral techniques which were recently introduced. They are like 5 years back. These techniques were first discovered and used by these authors in several papers. So this construction is the first that provides a truncation to maximal supergravity on a distinct non-spherical or hyperbolic background as opposed to previously known truncations. So all previous known truncations to maximal supergravity were on compact spaces which were like spheres or hyperbolic spaces or product spaces, not something like a fibered space. So this is, at least we didn't find any other example. So this is the first truncation to maximal on such spaces, which is not of like a sphere or hyperbolic or product kind. And our theory also contains the gauging of the global scaling symmetry of the metric, which is called the trombone gauging, and provides a concrete example of a higher dimensional origin of such gaugings. So this global scaling symmetry of the metric is a symmetry only of the equations of motion and not the action. So when you do a gauging, you typically lose a Lagrangian description, at least for some fields. And finally, once we have computed the spectrum and identified the short multiplets, we can compute the superconformal index, and we do reproduce the Hall-Littlewood index or Hall-Littlewood limit in large N that was given by Gadde, Rastelli, Razamat, and Yan. And this is the first holographic match of the superconformal index of class S from a supergravity computation. So like I described, since we have the full spectrum of light operators and we can compute the full superconformal index, we can, now the Hall-Littlewood limit we matched, but we can give predictions for the large N result for other limits as well. And that I'll actually show the result at the end. So now with those results in mind, let me go to the setup of under which we do our computations. So D equal to 5, N equal to 8 ungauged supergravity, which is maximal in 5D, has a global symmetry R plus times E6, 6. This R plus is the global scaling symmetry of the metric. And this theory can be gauged by promoting some of the vector fields or symmetry generators to the two non-abelian gauge fields. And the gauge theory contains further terms, like the potential, it contains further terms including covariant derivatives of 42 scalars, which are in the E6, 6 mod USP8. And there are some fermion mass terms and some scalar self-interactions. That potential we actually optimize to find the solutions. And which one?
Just maximal supergravity. So just Torus compactification of type 2 of type.
Yes. From the 11-dimensional perspective, is it also that same space, or it's like?
Yeah, we have a M theory on E6 or type 2 or type 2.
I see. Okay.
That's the theory.
Yes.
Theory is that one.
Yes. That the ungauged one is that one, right?
Yeah, ungauged one will just Torus.
Yes. Now, something about the whatever. Yes.
Why do we take this setup that ungauged? You want to gauge it and then show that this is the correct truncated version of.
Yeah, so like we don't want like the full N equal to 8 supersymmetry, right? We are the half. That's the description we want to get into. So that's why we gauge this supergravity, and ultimately we'll end up with a gauge group, which is the expected gauge group from the half maximum. 11-dimensional point of view, and most importantly the boundary where we'll compute the.
Isn't this the truncated theory? I thought like we have 11D some supergravity, then we compactify on E6 or something, then we get this one. But all the massives that we.
But this is not a theory you want. This is ungauged.
Okay, so now
The gauged theory is the one that is truncated.
Now I gauge it, and then eventually that gauge theory will be related to.
Yes. Exactly.
That is the theory which will put on the ADS 5 times whatever.
Yes. Exactly. Yes. So now for the exceptional field theory story, this is also like this about the same time when these spectral techniques were discovered. Actually using this where they found these spectral techniques. The gauge supergravity admits a redundant but convenient formulation with 27 vectors in the anti-fundamental and 27 two forms in the fundamental representation of E6, 6. In this formalism, the gauge theory is completely specified by the so-called tensor. These were the quantities I was talking about, X, M, and P. Here, these capital English letters, they describe the fundamental of E6, whereas the Greek letters, they describe the adjoint of E6. These small t's are the E6 generators in the adjoint representation. We won't go into much detail of what these capital theta and small thetas are, but I'll talk a little bit about this. Yes.
When you say area is completely specified, what is so let's say you give me this tensor.
Yes.
So now what do I do?
Like all the gauge couplings and all those are completely fixed once you are given the embedding tensor, you know all the details such as the coupling constants and so on. Theory.
There's some way which is to you take this tensor and somehow.
Yeah, that's the like how this works out is there are papers that describes in detail for the. Sorry, can you?
You need more than one theory, right?
You need more than one?
Ultimately, you need more than one theory. Because the different sigma will presumably give different supergravities on a case time, right?
Yes, the different sigmas will give different supergravities. Yes.
That information must be somewhere. And there is a completely specified. So what is the data?
You need a theta, you need some theta.
Yes, the capital thetas will be.
No, I'm just making it up. Is it really the case that the theta is what gives you the data of the compact Riemann surface?
Yes, because these T's are the generators of E6, so they do not depend. So yes, so the capital theta and small theta, they give information about the theory.
So what is X?
X is the embedding tensor, the thing that we will.
This is the definition of X.
Yes.
So you are taking X as a linear combination of the generators.
Yes.
E alpha.
No, not a linear. Here is quadratic.
Quadratic. First is linear, second is.
Here it's a quadratic.
The last one doesn't have any.
This X is not actually a number, it actually operates on the group. It's an element of the algebra.
Well, it's kind of the structure coefficient of the algebra.
So it's not
Structure
an
constant.
element of the algebra, yeah, I mean,
Oh, no.
not the real.
Theta is also an element. I see. Theta has an alpha index. So I suppose the
adjoint indices are objective, considering the three index tensor which are all indices are fundamental.
I see. So the N and P are all.
Yeah, M and P are the fundamental of E6. Run from 1 to 27.
Yeah. So you are taking a linear combination of
Yes.
E, then E square.
Yes.
Quadratic expression
Yes. Yes.
and E dependent on it, right?
Yes.
So this is an abstract element of not of the Lie algebra, but of this what we call envelope algebra. Because
The T, small t's, you mean?
the matrices and
Oh,
some
oh.
products, right?
Which one you are saying? The capital thetas or the X? Oh, yeah. Yes. They actually
And
behave
the
as
thetas and the G,
theta tilde, they contain information
they are
about the,
arbitrary at this stage.
well, they will probably contain the information about the compact surface. Yes.
So theta,
And
G,
theta
how many
tilde.
parameters? Theta, G, and that theta tilde.
What's G?
That's not, that's 9.
So that's 9.
Oh, this is 9. Yeah, 9 by 2. Sorry.
Theta and theta tilde.
Theta and theta tilde. Yes. They will contain
And
information.
why this particular form? Is there any reason? So how do you know that why not cubic term or other terms? Very tensor.
I think it's a definition, but well, we finally impose quadratic constraints to show that this X satisfies an algebra like this. So I guess that would be the reason why.
Oh, so claim is that object satisfies.
Yeah, the quadratic constants are imposed so that it satisfies this.
I see. So you construct
And these constraints have to be imposed because in the exceptional field theory we have introduced new variables, right? This is a redundant description, so you have to put constraints to.
But this is also not an algebra because right hand side has got terms indexes.
Like a structure constant, no? Like the x's.
Not structure because x itself has an operator. Right? Because it has a t alpha and t square.
Yes, yes, yes. Okay.
It's not a algebra in that sense.
So this is anyway not an algebra, it's some more complicated commutation because x is giving you
Okay.
x commutated and x gives you a quadratic operator in x.
In x, exactly. Yeah.
Yes.
I'm also confused why the q is not contracted when is it given to the left hand side?
No, no, no. Neither is M or N, right? Like
The two cubes on the left hand side.
so. Yeah. So here only the M and N index are different for the x's. These two indexes are same. That's the thing
Same
called
but not sum.
not summed. Yeah, the same. And you take the commutator of this, and that's how the R only the capital R is summed. Yes. Yes.
Not general commutator. Any particular.
Okay, maybe using the word algebra was naive, but the quadratic constant ensures that the x's satisfy a relation like this. Yes, because the exceptional field theory, like I said, it gets a redundant description in terms of vectors.
Or the theta and theta.
Yes, which one? Because yes.
Is here that they can be found or something?
Yeah, those details people described in this exceptional field theory. Mostly they have papers by Malex. Yes, yes, yes.
So basically, it's a set of algebraic equations for theta and theta.
Yes.
And there are some solutions.
Yes, 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 yes.
It's not completely clear to me because there's also the fundamental group structure.
Mhm.
So it's not completely clear to me that that's enough to satisfy it, but maybe it's but can somehow do something.
So what fundamental group
I mean,
structure?
there's also the group structure. No? The group structure is somehow changed on both sides. So if I just say I have some generators, I contract them with some theta matrix,
Yeah.
and then I impose some condition on the product of the generators, I might not be able to find any theta matrix that satisfies.
Yeah, I agree. Yeah.
So somehow this is it's non-trivial that such a theta exists, but finally just believe this.
Okay.
Yeah, because the left hand side, okay, left hand side will be at most cubic in.
Yes, so if both of them are the same order in X, so the generators are matching because they both have the same kind of order in X. But it's some non-trivial relation that you have to impose by matching every product of generators. You get a term which is quadratic in generators, that is cubic in generators, and also quartic in generators.
But left hand side probably will not have quartic in generators.
No, I think it will have quartic because theta tilde term will give you quartic.
But there's a commutator.
Oh, then we are in trouble.
So the quartic term has to vanish on the right hand side.
Okay.
Then you take care of the indices and everything. Maybe you're using the algebra of the T's itself as something.
Yeah, you have to, of course, you are using algebra of T's. The what is it? There is T and TP and TP. Their commutator will be TQ, right? We have three T's. Not four.
So maybe the idea is somehow this one of these sums over to give you some Casimir or something. This 3, the sum over R some sort to give you a Casimir thinking of some derivations. So then you get a number and which is some Casimir for the fundamental, and then you get some other.
Like the theta tilde being non-zero is the case where the trombone gauging takes effect. That's the trombone gauging is the okay. So the gauging of the global scaling of the metric, where you take the global scaling to that scale factor to be a function of.
But somehow you are saying that there is some way to solve the equations and get some theta solution for that.
Yes, yes, yes.
And that's important.
That's that those techniques are at least have been discussed in this papers by Malek and Samleman in this exceptional field theory.
But the parameters can be later described what you're going to get.
Yeah, those contain the information about the theory, yes.
And what does this constraint actually mean at the level of these theories? But this definitely restricts the parameters in theta and theta.
Yeah.
So what does it mean at the level of the theories you're going to get?
No. So when you're talking about this X and embedding tensor and so on, this like this exceptional field theory gives a description in terms of some redundant variables, right? It's a redundant but convenient formulation. So you have to put some constraints so that that redundancy goes away, right? Otherwise, you won't end up with the same thing. So the theta tilde equals not equals to 0 are the so-called trombone gauging, where the global scaling symmetry of the metric becomes gauged. And like I said earlier, this global scaling symmetry is anyway a symmetry of the equation of motion and not the action. So when you and not the Lagrangian. So when you gauge it, this actually becomes hard to write down a Lagrangian and so on.
But theta equals to 0 is also allowed, right?
Yeah, theta tilde equals to 0 is also. If theta tilde equals to 0, well, all these problems go away, right? Like quartic terms, those vanish because the quadratic piece is proportional.
You get a linear term. On the other side, you'll get a quadratic term. Actually, that might be even more serious problem.
In the commutator one, the linear term.
I see theta tilde is equal to 0. The whole second term vanishes. The first term just gives you a commutator of t with t.
Yes.
You just get a linear term. You just get f. On the right hand side, you have a product of two t's. Actually, that is a little worrying. How will that work? Product of two t's cannot give you a t.
But maybe you
It's like a sum.
use the Casimir.
Yeah, but even if you use a Casimir term, you cannot convert a product into a number.
Into a number, yeah.
So here the product has to get converted into somehow generate. Maybe, I don't know. Maybe if you look at it, yeah.
Yeah, there's a sum over R, so I guess that will have
Some
some.
people have worked this out and they.
Yes. And these kind of cases were described by these authors. So D equal to 5 supergravity that originates by truncation of D equal to 11 supergravity on the internal manifold sigma.
This solution for theta.
Yes.
If you have a gauge for gravity.
Yes. And this embedding tensor, the information of the embedding tensor completely fixes that.
Yeah. So is that the algorithm? What is the algorithm that you start with ungauged supergravity, right? Can you understand? This is just dimensional reduction of the
Yes.
M theory or PC sort of.
Yes.
To be straight, right? Starting from that theory, and after you have gotten these numbers, you can get it down. Right? What is the procedure that gives you the gauge supergravity? There will be some action of the gauge supergravity. Or some equation.
That will be contained in this capital theta and theta tilde, right? Like.
Can one take these thetas and just construct the action somehow?
Yeah.
I think he mentioned somewhere that the Lagrangian will construct in next.
That's when the case of theta tilde is non-zero, but at least in theta tilde equal to 0 case.
So you can write down the equation.
Yes.
Then you have to show that this is a consistent truncation of that term.
Yeah, so you compute this quantity, and in our case at least we observe that these are constant entries, like it depends only on the parameters, like I said. And when that happens, that this can be constant only for maximal supergravity, and that's how we know it truncates to maximal supergravity.
So these give an independent construction of maximal supergravity, right?
Yes.
Okay.
Well,
So far, this has nothing to do with
well,
constant. Right? You have to dimension reduce on a C.
Yes.
Right? So let's leave this. So this gives you general procedure for constructing the maximal supergravity.
For considering gauge supergravities.
Gauge supergravity.
Yes, yes.
Now can you say what you need to call your sigma?
Yes, yeah. So those, like the uplift, how we do this uplift to the 11D for the D equal to 5, that I have not included in the slides. That I left for brevity, but
Sigma related?
like for example, when you compute the like these thetas, this will contain information about the V, like the vibration thing V. That information in constructing those go in, and that depends on the Riemann surface coordinates and so on, right?
If you are reducing on a sphere versus a torus,
Yeah.
right? How will things differ? If you are chosen sigma to be a torus, you will get N equal to 4 square, right?
Yes, yes.
Is it possible to see how that comes from this?
Sure, there is.
Theta contains the information about the V that enters in the metric.
Yes, 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 yes.
B also the sigma.
Also the sigma.
Yeah.
Right?
Yeah,
I also
the
the metric one, so the sigma metric as well as the V one comes from the thetas.
Yeah, I think that's similar.
Only V will not suffice. V we get from this.
But the information on sigma also.
Sigma also.
The sigma is a modulus, right? So that modulus case information also has to go somewhere.
Like the information about the genus and so on. You mean?
Not just genus, the whole 60 minus 6 also a modulus case.
Okay, okay.
If your function is 60 minus 6, then
I see.
so all those parameters must be entered into these. In fact, the confusing
So the details.
part is that the number of parameters that you can get from sigma has no limit. You can get to arbitrarily high genus and then this 60 minus 6 will become very large.
Yes.
Right? So those parameters will have to enter in the race somehow or
I guess so.
all those. Because for torus, I know this modular parameter enters through the complex coupling.
I see. Okay.
Theta plus I over T square is basically the modular parameter of the torus. Okay, so in torus, it depends on the modular parameter is a parameter of the sphere. Then presumably for other Riemann surface also it will be the case.
Yes.
The modular parameter will be parameters of that.
Like when X is determined, that does determine all the couplings. I guess those will have the information of the moduli. But that will be through capital theta and theta tilde, I guess. But
Yeah,
the
the
details.
confusing part is capital theta and tilde.
Yes.
Seems to have a finite number. There is a limit of how many parameters you can get from that.
I see. Okay.
Maybe not all parameters of sigma are physical. Maybe there is some redundancy in the way you parameterize sigma.
Okay. Okay.
I don't know how
Okay. I see.
That relates to this gluing.
But each gluing will give rise to parameters. So the number of parameters of sigma is the same as number of gluing parameters.
So the manifold on sigma fiber S4 of the 16 supercharged solution. By 16 supercharged solution, I mean the Maldasan and Nunez solution that I showed. On the boundary of the ADS5, it will be 8 supercharges. It contains as a subsector the D equal to this, like our construction contains as a subsector the D equal to 5 N equal to 4 supergravity of Kasani, Waldrom et al. And they actually give the prescription of the generalized geometry framework for constructing consistent truncation of 10D and 11D supergravities, preserving various fractions of supersymmetry. The M-theory uplift of our supergravity model closely follows their prescription of how you do this. In this generalized. Yeah, the consistent, that's the thing that I said, the consistent truncation. Oh, you mean consistent truncation? I see. Yes.
When you look at the original M-theory and after reduce,
Yes.
you are throwing out very many fields, right?
Yes.
So how do you know that those field equations are automatically satisfied when the field equations that you are giving
like when you write down the potential for these 42 scalars and so on, that you optimize to get the solutions from the maximal gauge supergravity side, right? And you have to check that those are the solutions of these supersymmetry broken solution, like the half Mn2 and other solutions as well. That's how you would know, right? That these are contained in.
Take the original D for 11. It has some field.
Yes.
Right? And you have to show that all those field equations are satisfied. When this D equal to 5 supergravity field equations are satisfied.
Yes.
Right?
Yes.
So the number of field equations for D equal to 11 supergravity is
Not?
Is a lot more.
Yes. Right.
So you have to check that all those equations automatically are satisfied.
Yes.
So what is the general technique for doing that?
Okay. I see what you mean.
You are saying that it's a consistent truncation.
I think this generalized geometry framework can be used to indicate that, or at least see how that works out. That's at least in their case, they do this generalized geometry framework to find the different solutions, like which preserves like various fractions of supersymmetry and so on. So this generalized geometry framework has a technique which does this.
It's a different framework, not related to the embedding tensor that you discussed.
No, embedding tensor you will calculate, but the framework by which you compute, use the generalized geometry framework and
use this generalized geometry framework to compute the maybe the embedding tensor.
Yes.
If they satisfy the constraint that
Yes. Like you use the generalized geometry framework to compute the x's and then see if has the required properties and so on. That's how you know. Yeah, the details of the uplift I have omitted for brevity of the talk. So let us now describe the spectrum. So first what I'll do is that I'll describe the approach that was used by Bhattacharya's test to just solve, no exceptional field theory, nothing, just solve the Klein-Gordon equation to get the Kaluza-Klein masses of the gravitons. This will do to like, check with our result from the exceptional field theory side. So in this approach, it is we solve a Klein-Gordon equation in the Einstein frame metric with the overall warp factor e to the 2a to get the Kaluza-Klein graviton spectrum. And for 11D supergravity, this is the differential equation that one has to solve. This G6 is the 6-dimensional metric of the compact space without the warp factor. That is stripped of the warp factor and sits out. And like for our purposes, the 6-dimensional compact matrix we'll be using is that of the Maldasan and Nunez solution, because we want the Kaluza-Klein spectrum about that vacuum, right? So, and that's the G6 we'll be using. So this is the warp factor if you see the Malus-New's metric again, you'll see that this is the warp factor. Delta tilde is given as a function of this. And with this substitution, u equals to cos square theta, and taking this answers, one can show that the differential equation, this differential equation takes the form of phi times a hypergeometric piece for HU plus a piece which is proportional to this, the HU times this quantity. Now, this operator that we have y squared del 2 del x2 plus del 2 del y2 plus 2y ny del x, this is the operator that occurs when you solve for a charged particle moving in a constant magnetic field in a hyperbolic background. This one? Oh, this one?
Yeah, can you just solve the spectrum of fluctuations in this truncated spectrum?
Yes, for the graviton.
For the graviton.
Yes, yes. From that you get this.
But there are other fields, right? You have to solve.
Yeah. So we solve for this one to match the graviton spectrum from the exceptional field theory side. But for the other fields, we don't want to do that because you have to solve complicated differential equations, which is circumvented by having this exceptional field theory story, which gives you the spectrum of the other fields more easily. So this computation I'm just showing, or like we have to do because we wanted to match. At least we have, so that we have something to match. Yeah, and from the linearized
of the various fields. But the solution you have to find, right? What is the?
But from the linearized fluctuations of the equation of motion, don't you get the?
You get the
Kurzweil-Klein masses. Yeah, that's how we get. That's how we get the.
How does the exceptional field theory help in getting this? I thought you got the equations of motion from the exceptional field theory.
Okay.
Right.
But only, like say for example, if we compute the x's, that fixes the solution for us.
Pregnancy is not possible, but still you can get the equation. That's what you have said.
Yeah, that's the exceptional field theory here, right? Now, for the metric, you are giving the solution. You are solving it.
Yes.
So, what is the argument that you don't have to solve it for the other fields?
Okay, so it gives the equation of motion and we get the potential, right? So optimizing the potential, we get the solutions.
That's the vacuum solution.
Yes, vacuum solution. Yes,
Vacuum
yes.
solution.
And the linearized equations of motion about that vacuum will give us the spectrum. Yes, yes. And for maximal, that's what we'll show that for the maximal case, the maximal supergravity case, these from the linearized fluctuations, what you get is an algebraic relation for the masses.
The next equation is supergravity. With six-dimensional compact metric.
This one, yes.
And for your supergravity, that was all gone. Have you already done this reduction?
No, so here this is a separate exercise so that we can match the exceptional field theory with a known result. That's why we are computing this one. Yes, the metric is like we used to.
Hyperbolic metric.
Yes.
Oh, it's just hyperbolic metric everywhere. Oh,
Yes.
It's the uniformly hyperbolic.
Yes.
Okay, so you are solving this equation to match which exceptional field theory will correspond.
Oh,
That's what you are saying, right?
yes, like to match, yes,
But
in some sense, yes.
What?
Yes.
Solving this, looking at the spectrum, and then that spectrum will match against the
Exception, at least we'll match the graviton spectrum with the thing, and then for the other fields, we'll get the. Yes.
Somewhere along the way, so somewhere the moduli should matter, right? Even if it's hyperbolic, you can put some hyperbolic metric, but the moduli should be important for the source.
Yeah, so G naught should contain information about the moduli.
The G naught.
G6.
Right?
G6.
G6, yeah, correct. Yeah, all right.
So, okay, so we get,
Not G6. Correct. I thought it's G2.
no, G6, the full,
G6,
the metric on the full compact space.
Now, I'm very confused. This G6 you don't go in detail. Maybe you're saying you can write down locally hyperpolymetric everywhere, but then the moduli have some very complicated form.
Okay, I see.
Because the structure of this manifold is some complicated manifold, but some about where you're going to get a pair of lines.
I see, okay.
Sorry, I'm asking a very simple. Is it actually possible to solve pole in any realistic way?
Solve what for?
Can you solve this equation in any realistic way?
Yes, that's what we're doing here. Yes, we do put this metric on the Riemann surface. Dx square. You're saying that this shouldn't be true everywhere. Is that what you're saying? Yes, yes.
So your sigma 2 is not just the upper half plane, but this metric you would put in the upper half plane.
Yes.
So somewhere you want to say it's not the upper half plane with some pair of tiles or something else. So you can always put this metric.
Yeah, so yeah, locally you can put this metric, and that's what we are solving for, and the consequence. What?
There will be quotient of this by some Fuchsian group to get the general Riemann surface.
Well, for the upper half plane, this operator has a discrete part, which is this, and a continuous part. For compact, it won't have the continuous part, right? Because it's a compact surface. No, so for this solution, we forgot to mention the references. But for the discrete spectrum, these are we get the eigenvalues, this and these multiplicities. This is some works in the maths. And
you see that metric that you wrote
Mhm.
is not enough to specify sigma.
Yeah, right.
Because that metric you could have just put in the upper half.
Yeah, so this solution is just in the upper half. What I did there.
But the eigenvalue should depend on what the manifold is.
Yeah, so in this case, manifold is upper half plane.
Yes, yes.
So, but then that is not the kind of manifold you want to consider.
Yeah.
You want to consider pair of manifold. That's like three punctures, some three punctured sphere.
Yeah, on three puncture sphere, you can put hyperbolic metric. Right?
Three punctured sphere you know how to do, but for the general, so is that what you're trying to solve? Three punctured sphere?
No. Riemann
Just
surface
take
genus G.
genus to
Yes. Yes.
Genus to surface has 6 modules.
Yes.
Where is the information about that modulus going?
Yeah, we didn't. Yeah, this was a caveat.
See, essentially, for example, there are these papers which try to find the eigenvalues of Laplacian on Riemann surface.
Yes.
And there are these various kinds of Riemann surface, and the spectrum does depend on what Riemann surface.
Well, the multiplicities do depend on the genus.
It's actual eigenvalue.
Okay.
Right? This Sridip and Mazak and the various people I think wrote these papers of just eigenfunctions of Laplacian on Riemann surface.
I see.
Right?
Even in the simplest case of just a torus.
I think torus is probably not included in this because it's not hyperbolic.
Yes.
Right? So genus 2 may be the simplest one.
Okay, so you take a pair of panels, you glue together, but it's clear that it should depend on the module.
Yeah.
Laplacian should certainly depend on that.
Yeah, this was one of the things like we mentioned in our paper also, but this regarding the moduli, the understanding is not completely.
Ultimately, the point is if you are calculating superconformal index, presumably those dependencies will go away because
Yes.
variation is
Okay.
superconformal index.
Right.
But at this stage, if you are just trying to understand the spectrum, that should depend on the modulus of the universe.
Okay. I see.
Because what you seem to be saying is that you solve this in upper half plane, and then for genus you multiply by sigma.
Yes.
The last class is that the multiplicity is given by that.
Yes, this was, I think, some papers in algebraic geometry. No, not. What was the?
Maybe are you saying some of the index and some?
No, the index doesn't depend on the moduli, no?
Yeah, index should depend on.
This also doesn't.
Yeah, this formula doesn't
This
depend.
answer doesn't depend on this. Are you saying for the index, we effectively use this formula or something?
Yes.
Like going to some point in modular space, you can always go to some, maybe, are you saying that you solve it for upper half plane, and then you take some other non-trivial surface. There's some point in modular space so that you get the same spectrum as the upper half plane, but with this degeneracy, with this multiplication. Maybe that's what, are you saying that?
Yes, like from the papers that we went through, or like we could, what little we could understand is that for upper half plane, you have this spectrum plus a continuous spectrum. But when you put it on a when it's not an upper half plane but a compact surface, you do have this and some discrete and some other discrete values of the eigenvalue. It cannot have a complete continuous spectrum because it's no longer the full upper half plane, right? It's a compact. Yes, I guess so.
I'm saying that you can consider these eigenvalues with this multiplicity.
And this multiplicity, like this eigenvalue and multiplicity was for compact Riemann surfaces. That's what we understood from the papers we went through.
There is some point in modular space that the equation simplifies and you get this multiplicity. Like
I would guess that would be the answer, correct way to think about it.
That probably like to do this pair of trans decomposition, maybe degeneration limit.
Yeah.
Where
Okay,
this
okay.
has become a pair of points connected by round.
And that's right.
And within that limit, we get the eigenvalue.
I guess so. But thank you for suggesting those papers because we didn't find much on this topic. So yeah, sure. I'll be finished in time. So altogether, like once you take that, once you take this differential equation to be true, altogether we get a hypergeometric for the function hu, and demanding regularity at u equals to 0 and u equal to 1, we get the discrete spectrum, which is given by equation 5. And here I would attract your, I want to mention something that the fact that there's a topological S4 is denoted by having this kind of, this K is the Kaluza-Klein spectrum, and we have a eigenvalue part, which is K into K plus 3, which is like a 4-sphere eigenvalue. And then for the R charges, which is for n equal to 2, it's SU2 cross U1. And that's what we get here. So SU2 is L into L plus 1, as it is, and n square is the U1 part. And this last contribution is the effect of the fibration. That captures the effect of the fibration for which we get the mass Laplacian and so on. And more importantly, it captures the universal deformations of the Riemann surface. So for the spectral, so now we use the spectral techniques mentioned earlier to calculate the masses of the other fields. So having a truncation to maximal supergravity allows us to compute the masses of the other fields algebraically instead of having to solve differential equations for the other fields as well. We match the gravitons there. This is why we did the Bacchus's test exercise, that we match the graviton spectrum opted from the exceptional field theory side with this result to make sure that we're on the right path. Now, given a compact-to-wide supergravity solution that preserves some supersymmetry, we know that the particle content of the theory must be in representations of the unbroken R symmetry group, which in this case is SU2 cross U1. So first what we do is we compute what are the allowed supermultiplates that can be, and that can be determined by the representation theory, and it has been done by various people and so on. And at each Kaluza-Klein level, once we get the spectrum of all the fields from the exceptional field theory, at each Kaluza-Klein level, we allocate the different fields with the corresponding masses or conformal dimensions, whatever you have, along with their multiplicities obtained from the exceptional field theory computation to fill out like a subset of these allowed multiplets. And that will give us the light operator spectrum of the theory. So here is the statement I was referring to, that the linearized exceptional field theory equation of motion, linearizing the exceptional field theory equation of motion, we find the mass matrices, which are given like for gravitons is the thing. This M is the matrix of those that contains those 42 scalars. Like I said, each entry depends on the scalar. This V that occurs for gravitino and for fermion mass matrix, this is roughly the square root of the scalar matrix, which is V transpose V is M. And these curly T's are the generators of the whatever symmetric group is this sigma times S4. If there was no sigma or the effect of sigma was just dropped, then this will be simply SO5, which is the symmetry group of the S4. And when I say this, what I mean is that the SO5, it is embedded in E6. So the adjoint of SO5 is contained in the branching of the fundamental of E6. So this M runs from 1 to 27, but out of them only 10 are non-zero for the SO5 case at least. 10 are non-zero, rest all are zero. And these curly T's must satisfy this algebra, where these X's are the embedding tensor antisymmetries. Well, that I flashed just to give you an idea that what goes into computing at least the mass matrices. So here's the Kaluza-Klein spectrum for at KK level like 0, 1, 2 up to whatever. It consists of G minus 1 copies of these multiplets that I have here. And the last line, this line where the long multiplets are, these are present only for k greater than equal to 1. And when you have n equal to 0, j is equals to 0, and this plus prime denotes that the n changes in steps of 2. The dimension, what I've written here, E, K, L, and J is this. This is basically 4 plus m square L square, what we had from the Bacchus stress thing. And here I've used one slide to just to give the.
Can I ask a question?
Yes, yes.
Okay. This spectrum that you just showed us, okay, you're saying that you got it from exceptional theory, but if I just used U duality, okay, which is kind of what this exceptional theory is supposed to encode, like could I have gotten the spectrum, this, how much of this could have gotten, like, this 6?
From U.
So if I just take the graviton KK spectrum and say that I should complete it to something which is U duality invariant, some E66 invariant, then would that give me this, or would it give me only parts of this?
Well, this formula EKLNJ that I have written here, the equation number 7, that you get from the graviton, and this is the formula for, like, ultimately the formula that governs all the conformal dimensions. Is that what you are saying, referring to, or?
That is fine, but I'm just asking that what is the, like, what is the content of this? How much of the spectrum I could have gotten just by imposing U duality, right? Just by imposing E66 invariance. I mean, I understand that you guys have tried to work out the whole equations in some U duality invariant field theory, okay, this exceptional field theory and so on. But if I just don't do that, if I just kind of try to just look at the spectrum of Kaluza-Klein gravitons and try to make it, add things to make it U-duality consistent, would I get this thing, or is it?
Will it also work if like the representation in which the particles are is SU2 cross U1, like a subgroup of E6? Like all these particles are in the representation of SU2 cross U1, right? So it's only a subgroup of
E6. Maybe let me phrase it differently. How does E66 act on this spectrum in 6? Does it act on this, or?
In your case, what is the final group of the invariance? E66. E66 has been broken down, right?
Yes, the two down to SU2 cross U1.
Yeah, down to
SU2 cross U1, which is the R symmetry.
The question is, I'm using the SU2 cross U1.
Yes.
Right? You can presumably restrict the spectrum of the theory, right? Or
maybe restrict, but I don't know whether we'll get the masses of all the fields. Would that be?
Can you check the SU2 U1 invariance of finance?
Yes, that we can check. Like for example, at Kaluza line level 0, like at the Kaluza line level 0, for SU2 cross U1, we will need 4 massless gauge fields, right? So that you can check that in A2 bar for k equals to 0. In A2 bar, you have a triplet and a singlet vector, which are the
spectrum is automatically invariant.
Yes.
Yeah, this is probably like the 8 supercharge superconformal representations, right?
Yes,
these things that
exactly.
Okay, I'm not familiar with the notation, but I assume so. So you're saying each of them is a superconformal family by itself.
Yes, superconformal.
In the supercharge, 8 supercharge superconformal family. Like in the n equal to 2 4D n equal to 2 superconformal family.
Yeah.
Which has 8 charges and 8 whatever
yes.
Super like conformal charges. Is that the point? That so that you have written it in that way, right? Is that
like the LL bar are the long ones and these are the short ones of different.
Okay, but now I'm just trying to understand how does the E66 do that? So E66 does it act on the spectrum? Like, does it mix these superconformal families?
The E66 gets broken already when you gauge. Right? Because you have only gauged E66 subgroup. E6 is broken. So that is already broken E6. You may not have.
Okay, so that is. But I thought this exceptional field theory, you can see this E66 acting more clearly, right?
Yeah. So what I'm saying is that I think E66, I mean, the original theory had an E66 invariance, the torus compactification. But after gauging, I think E66 is not a symmetry anymore.
Yeah, some of it will be broken.
Yeah. And what he's saying is that only the SU2 cross U1 part is unbroken.
Yes.
Of that E66.
Okay.
That's how I understood from what he said.
Yes.
So the SU2 times C1 is a subgroup of E66.
Yes.
So this came from E66.
Yes.
Let's see. Yeah, so for
so that
perhaps you cannot get anything more than SU2 times C1 representation.
In that case, how does this exceptional field theory thing work? It's a bit, I'm not following these details, but so you're saying that, like, what is the information you put in, into this exceptional field theory to get the spectrum?
Well, we do.
Like you said, you don't have to solve differential equations, but what did you put in?
Like when you do the generalized geometry framework, you do put in the information that there's like S4 coordinates and the sigma coordinates. But the information of the moduli, how that goes in that, I'm not very, like I'm still not, don't have the full understanding about it. But when you do the generalized framework, that's where all this information goes in, that what surface you're compactifying on and so on.
Sure. Okay.
Like
but how does it go? But how does it go in? Because you're not solving differential equations.
No. Yeah, so if there was not a truncation to maximal supergravity, one would have to solve some differential equations, but the consequence that is the consequence of the fact that it truncates to maximal supergravity allows us to compute the spectrum without having to solve differential equation and just get it algebraically.
Okay, so maybe what you're trying to tell me is that you just take the maximal supergravity, okay, and you just kind of decompose it into SU2 cross E1. You take the E66, the full E66 thing, and then break it up into SU2 cross E1. Is that all?
Exactly.
Okay, that's what is. Okay. So you just take the, so there's some argument that basically maximal supergravity multiplets all just break up, and you're just taking the full multiplet and just breaking up into SU2 cross U1 multiplets.
Yes.
But how do you get equation 7 then? That you have to solve some differential equation, right?
So once you get the mass spectrum, like m square L square, then you just use this, you use these relations between the conformal dimension and m square L square to get that relation. This is straightforward. Like once you m square L square
No,
hand side of 8, you can just solve.
So you should either know delta or m square, right? To use this equation, you should either know delta or m square. I understand these two are equivalent, but how did you know either of them without solving? But you wrote down some differential equation and saw the Casimir. Is that the point?
Yeah, the differential equation that I showed was the Backus-Stes approach to get the graviton side. That we did so that we can match with the exceptional field theory side, at least the graviton spectrum, so we know which solution and what, like we are at the right solution.
Okay, but you had the spectrum independently, or did you read off the spectrum from this Backus et al. And use it?
The spectrum we worked out independently from the exceptional field theory side.
Okay. Yeah, so there you just look at the differential equation and you just read off the Casimir. Is that how you read it off the? See, I understand you break up the maximal supergravity multiplet.
Yes.
But then you have to know like some spectrum, right? Like how do you get? Could you just go to the Casimir? Could you just go to the slide where you had this multiplet?
This one?
No, where you had the superconformal multiplets.
Oh, superconformal multiplets, I see. This one, yeah, okay.
Right. Okay, maybe this is. Okay, this is probably just some Casimir equation that you use. Okay. Doesn't have any moduli in it. Okay.
Yeah, so I showed this slide. So now I'll talk, that's the last part. So we talk about the superconformal index. This is a superconformal index is given by this quantity where this rho, sigma, tau are some fugacities. These are used to refine the index, because otherwise, if you don't have these, like all of the short multiplets will just give you some contributions and you'll end up with some pure number. You don't know which part is coming from which. So that's why you use these fugacities so that you know precisely which contribution is coming from which short multiplet. So these deltas are like some anti-commutators of QQ dagger. I've used a particular delta here. You can use other deltas also, but that will determine which deltas to use here, because these should commute with delta 1, like whatever you're using here. So it's a particular choice. So now that we have the spectrum, we can compute, and this is the superconformal index that we get. And we can we can see that the Hall-Littlewood limit gives us the result. This is the exact result that was obtained by Gadde, Rastelli, Razamat, and Yan. And you can go to other limits, and from this formula, you can just give the predictions for the other ones, like I promised. So I'll just end with a couple of future directions. The natural question that arises from the analysis is whether this story of truncation to maximal supergravity generalizes to other supersymmetric solutions as well. Currently, we are trying for the n equal to 1 cases, and we do have some success. Hope it will be out soon. The next one is probably a bit more ambitious, but I kept it anyway because it's an interesting direction. Is that we have the n equal to 2 superconformal index for light operators. It will be interesting to see if one can figure out the index due to the heavy states as well. This is like ambitious future direction, but I've just kept it because the interesting direction to pursue. And with that, I'll end my talk. Thank you for attending and paying attention.
Okay. Are there any further questions? Okay. So if not, then we can thank Ritabrata for the talk again. Thank you.
Thank you. Shall I just disconnect the call or shall I just disconnect the Zoom call?